So this is chapter 19, all about spectrophotometry, but we're focusing on the instruments and its applications. This is all about the spectrophotometer, but it's part 2. So this was the generic, the generic diagram of a single beam spectrophotometer. And in part 1 video, we went through the light sources, some options for that. There were 3 that were very important. If it's a UV vis, which means it works in the ultraviolet and the visible range, there are 2 options for light sources. There is the xenon flash lamp, which works from pretty much, I think it was 110, now I don't trust myself, to 2000 nanometers, meaning that one lamp covers the entire spectrum of UV and vis and beyond. But that's all we really are caring about here. And then the second one is the tungsten lamp, which does like 320 to 2500 nanometers. And then we'd have to combine that with the deuterium lamp, which is like 110 to 400 nanometers. You don't for the xenon flash, I care much less that you know the range, other than you know that it's the entire range of UV vis. For the tungsten and deuterium, that would be important to know the range of those two because they have to go together. It's not possible to cover the entire ultraviolet and the entire visible spectrum with one or the other lamp. Deuterium is the beginning of the UV, and just the very tail end of the UV is picked up by tungsten, and then tungsten handles the rest of the visible spectrum. And then for IR, the silicon carbide glow bar is the source for the IR, and there's just one. That's the only one I'm asking you to know. So that would be for a spectrophotometer that works only in the infrared range. We do not see one instrument that does all 3 of these. We see IR, or we see UV vis. Now, I guess something that I should have mentioned, I didn't mention in the last one, we also have instruments that are just visible. Okay, the reason why I didn't call those out specifically, because typically those are just white light bulbs, like the kind of light bulbs that you use, at home when you put a screw light bulb into one of your lights, because that lets off the entire visible spectrum as well. That's why part of why those instruments are so much cheaper than the UV vis and the IR, because we can change those suckers out. We just got to buy the tiny ones. So I didn't mention that, and I should have. I was focusing kind of on the more expensive technical side of it, that in industry you would use a nice UV vis instrument, not one of the little countertop buddies. So anyway, check. We did light source. We're going to talk our way through the monochrometers. By sample, what I mean is the cuvette. We're going to talk through the cuvettes, which are the containers, and then we're going to talk about the detector. And so it's going to be important that you know in general what each of these parts do, and then the information that I tell you about how they work. There's a lot more to these than what we're going to talk about on some of them, the monochrometer and the detector. For the cuvettes, there's not much more than what we're going to talk about. But be prepared to talk about those. Okay, so we're going to start with the monochrometer. The purpose of a monochrometer is basically to filter out all the wavelengths of light coming from the light source, because, I guess I should have mentioned this, these numbers that I wrote in parentheses, when I turn on the deuterium lamp, it's letting off all of those wavelengths at once. When I turn on the tungsten lamp, it's letting off all of those wavelengths at once. When you turn on the lamp, it's just like turning on the light. It doesn't filter it, it just lets off all the colors. Okay, so that's what the purpose of the monochrometer then is, to filter out to the one wavelength that you select. Okay, so there is in the monochrometer the entrance and exit slits. So the entrance slit is where the light comes in from the light source. So all the wavelengths are coming in the entrance of the monochrometer. And by the time it reaches the exit, which is where the light leaves the monochrometer and moves on to the next step, by then, that's when it needs to be narrowed down to just the wavelength that has been selected. And so all of that other wavelengths of light need to be trapped or sent back out of the monochrometer. We're filtering it out, everything but that one wavelength. But it doesn't work like a filter, like when you're filtering solid from a liquid. I mean, that's not how light works. So that's not how we're going to look at it. There has to be some sort of dispersing medium, something that's going to separate the wavelengths from being just all jumbled up together, all their different colors, to separate them out to just the one that we're looking for. There are a couple different types of dispersing mediums. I'm going to talk to you guys about one. We're going to talk about one type. And that's the one that I'm going to hold you accountable for. For those of you that are chemistry majors, when you get on to instrumental analysis, which is like the end of quantitative analysis, the second semester of it, but it doesn't happen until pretty much your last semester before you get your bachelor's degree. You'll get into more detail, but we're starting out here. So the type of monochromator we're going to talk about are the ones that are made using diffraction gratings. So a diffraction grating looks kind of like stair steps. So it's on this picture. It's the blue, this. Okay. So what happens is the light is coming in from the entrance slit and it's doing all of its wavelengths of the light that's coming in from the lamp. And what happens is it's going to hit the stair step thing and then it's going to bounce off of it. Now, in our textbook, it goes into the angles and it goes into all that. We're not going to do the trig that goes along with this to figure out the angle of the incident light is the light coming in, and the emerging light is the light that once it bounces off of that. We're not going to get into that. But just believe me when I say that these gratings are made so that way when the light hits it, it will bounce, so that way each wavelength of light is coming at a different emerging angle. So this one might come here, this one might go there, and this one might go over there. So it's separating them. Okay. And then what's going to happen is we're going to keep doing this, filtering them out until we can get a stream of just the one wavelength of light that we want. And then the grating will adjust itself so that is the only stream of light that makes it through the exit slit. So like if this is the light, this is the wavelength that we want. It will angle it. So that is where the light has to leave to move on to the next step. That's the only wavelength that can fit there. This wavelength will go somewhere else, and this wavelength will go somewhere else. So this diffraction grating, it moves based on the wavelength that you set the instrument to be. Okay. So in words, the polychromatic radiation is what I'm saying is the light coming out of the light source, the lamp. Okay. It's all the wavelengths that the lamp lets off are all coming in. It's collimated, which means made into one ray, okay, by a mirror, and then that strikes the diffraction grating, and based on the wavelengths, it emerges from the diffraction rating. It bounces off the grating. So each wavelength is separated into its own stream. So each wavelength is separated for its own stream. And then there's another mirror that will help take the wavelength of light that we are interested in and get it through to the exit slit where it goes on to the next spot. Okay, so only the wavelength that we select is able to leave. All of the other wavelengths they use mirrors to separate them to where they do not go out the exit slit. Okay, so this diffraction grating obviously has to move so that way it can, and so do the mirrors, to angle this correctly. So it's just a bunch of, well, reflecting light off of mirrors and this grating to get it to go where you want. Okay, so if you've ever played with like a laser and a bunch of mirrors to try to get the light to go where you want, this is literally what a diffraction grating is, other than at one point it's not just a mirror. It is this stair-stepped shaped item that separates the light. So it's kind of like a prism, but not like a prism because a prism is another type of monochromator. But like when you shine white light into a prism, like a piece of glass, and then you see the rainbow coming out of it where it separates it, that's pretty much what this diffraction grating is doing. It's just in a stair-step pattern, and it's not a prism, but it works pretty much the same way where it separates it. And then we filter out using mirrors the one color that we specifically want. Okay, so this is more what real life it looks like. So this will be where, like, light bulb. Let me draw. There's my light bulb with all my colors of light coming out of it. And they go into the entrance slit of the monochromator. And then it hits this mirror, and the mirror directs it to the grating. And then based on where the mirror and the grating are arranged, all the different wavelengths come off to different angles hitting that mirror. And that mirror adjusts to let only the stream of light that is the wavelength that we want to go out the exit slit. All other wavelengths of light would go bam, 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 bam. They run into the sides, so they're not able to go out to impact our sample. Okay, so that's our monochromator. The only type of monochromator we're talking about are diffraction gratings. And I would be able to explain to me a little bit about how that works. If you need to draw a picture, that would be great. If you want to use words, that would also be great. But be able to answer some conceptual questions about how a diffraction grating works, and that knowing that it's a monochromator and the purpose of the monochromator is to filter out the light except for the one wavelength. Okay. So this is just giving you an idea. So I showed that picture of, light source, monochromator, cuvette, detector, computer. Yeah, in real life, it's not like a giant rectangle, isn't what happens. So this is just an image of the inside of the current instrument, or no, it's not actually our current instrument, but there's a lamp, and then it goes into the diffraction grating. Or sorry, I lied, not yet. There's the lamp, and so they're just using the mirrors to get the light to go where it needs to go. It goes into the monochromator, where's the diffraction grating and the mirrors, and then it goes out, and then this is just getting the light, again, aligned where it needs to be. This one is a double beam, so we see two lights, one's the reference and sample. And so we're going to talk about those, which are the cuvettes, next. And then we're going to get to the photomultiplier tube. That's our detector. That's our last thing. So those are what we have left to talk about. But you can see that this isn't just a straight line rectangle. They have to fit it inside of a relatively moderately sized instrument. Ours looks much smaller than you would expect based on the straight line picture. So this is just showing you they still go in that order, and I wouldn't expect you to draw this elaborate of a picture. I'm looking for, sorry, I just about wrote on the screen with a regular pen. The picture that's just rectangles, that's enough for me. So again, that's kind of the view of an inside of a spectrophotometer. I just think it's kind of cool to see how it really looks. So what we want when we're talking about the monochromator is there's a trade-off between getting good resolution and a good signal. So what that means, getting a good resolution, meaning if I said 510 nanometers, only 510 nanometers makes it out the exit slit. Versus signal, which means strong intensity of light. Of that wavelength, there's lots of light, enough light that it's going to make really great measurements because a lot of light is shining into my sample. Well, if you make your resolution worse, so instead of 510, you're like, yeah, I'm okay if it's like 507 to 513. If all the light that comes out of the exit slit is in that range, that's good enough. What we're going to do is we're going to get more light coming out. It's a bigger range. So we're going to get a better signal. Our absorbance values will be higher because we have more light shining at it. But then we lost the resolution. We know that it works best at 510. And what I've done is I've opened that range up. So there's this happy medium at finding the bandwidth, which is the distance of the like the error ranges of the wavelength of light that it's selected versus the amount of light that comes through.